And thanks for the introduction. I'm very glad to give this presentation, and it's my pleasure. And today, I want to share the topic, Physical Simulation Technology, Ansteel, Gleeble, an efficient platform for material research. And I'm from Iron and Steel Research Institute of Angang Group. And first, I will introduce Ansteel briefly, and then I will share my view on Gleeble. And next, I will present our research on metal forming process simulation by using Gleeble. And finally, I will share our work on expansion of Gleeble. Now, let's get started. Ansteel is located in Anshan City, Liaoning Province. That's in northeast of China. Let's take a look at the map of China. And here is Ansteel, and this is the location. And Ansteel is the cradle of steel industry of China. About 1/4 area of this city is Ansteel. And so the city has got another name. That is the Steel City. And there are several research institutes in Angang Group. And Iron and Steel Research Institute is just one of them. And this picture presents the profile of our institute in the future. It's not finished yet. And this is the main building. It's to be rebuilt. And this is the sticky laboratory. It has been finished. It has this appearance now. Okay, let's take a look at the main building of our institute now. And this picture shows the appearance. And there are several departments in this main building that will deal with different kinds of products and processes. For example, the iron making and steel making, the hot rolling, the welding, heavy plate products, automobile steel products, and etc., etc. And here I cannot name all of the products and processes, because the development of the products and processes in Ansteel have been always in progress. As I mentioned above, there is a sticky laboratory, and the full name is the Sticky Laboratory of Metal Materials for Marine Equipment and Application. And we perform our research mainly in this laboratory. Okay, let me introduce the Gleeble systems in our institute. And first, we had Gleeble 1500. That was in 1980s. And then we had Gleeble 3800. And this simulator has 3 mobile conversion units: the universal system, the Hydrawedge system, and MaxStrain system. That was in 2003. And now we have Gleeble 3800, Gleeble touch control system. And this simulator has an attachment. That is the induction heating system. Okay, let's take a look at the profiles of the systems that we have. And this is the Hydrawedge system, and this is the MaxStrain system. These are 2 mobile conversion units. And the picture to the right is the induction heating system. It's a new technology of DSI. It's really a good idea to attach the induction heating system to Gleeble, because it's more convenient for us to perform the uniaxial compression test by using this system. And in the following parts, I will show you the details. Okay, my view on Gleeble. In general, it is called thermomechanical simulator, because there are mainly 2 closed-loop control systems: the temperature control and force control. And with these 2 control systems, 3 parameters could be controlled: the temperature, force, and displacement. Generally, we say it's stroke. And with these 3 parameters, and we can control the test. Now, let's review Gleeble series briefly. Originally, there is only thermal control in Gleeble system. That is Gleeble 500, which aims to simulate the welding process. Let's take a look at the picture on the top. And this is the Gleeble 500. And then, with the development of the technology, the thermal control can be combined with mechanical control. And that means the temperature and force could be controlled at the same time, and which make it possible for Gleeble series coming to us. And for example, the Gleeble 1500, 2000, Gleeble 3500, 3800, etc., etc., and which could be expanded to more fields. Let's take a look at the picture at the bottom, and this is Gleeble 3800, Gleeble touch control system, and this is what we have now. And Gleeble can be used in many fields. Since I'm from the steel company, I just introduced the application in steel industry. And our research are mainly divided into two parts. The first part is to develop new products, and the second part is to develop new processes. And once the steel has been designed, and with certain chemical composition, and the following things should be known first. For example, the casting process, the reheating process, the mill capacity, the rolling and cooling process, etc., etc. And these things should be known first to produce the steel. And in general, we have three ways to develop new products and processes. And first, we can perform our research on the real production line directly. And this picture shows part of the production line. And to make it smaller, and we can perform the research on smaller rolling mills. And this is in a laboratory scale. And to make it more convenient, and we can perform a test on a Gleeble system. Since we know the Gleeble can heat the sample to a specific temperature, and after holding there, and it can be cooled down to deformation temperature. And after deformation, it also can be cooled down to the room temperature. And this process corresponds to that on the production line. And so, Gleeble is not just an equipment. It also could be regarded as a macro production line. And this is my view. Okay, now let's make a comparison between the test on the production line and the test on Gleeble system. And for the production line, we just use the billet with dozens of tons heavy. It's really so costly. And the test period should be counted by days. Well, compared with it, the test on Gleeble, we just use very small sample, only has the size as your finger. And the test period could only be counted by days, by minutes. So it can be concluded that by using Gleeble system, we can cut the cost and shorten the developing time. And this is why we should perform a physical simulation test. Okay, let's take a look at this picture. And this picture shows the production line. And in this picture, I want to show you what we do with Gleeble and what physical simulation test we do. We just start from this process. It's a continuous casting process. And we simulate this process to get a proper bending temperature and to avoid the cracks at the surface of the billet. And in the following parts, I will show you the details. And after this, the billet will be transferred to the reheating furnace or transferred to the rolling mills directly. And in the reheating furnace, and we can simulate the reheating process to get a proper reheating temperature. Because lower reheating temperature will contribute to smaller outstanding grain size. And the lower reheating temperature also means energy saving. And after this, the billet will be transferred to the rolling mills. And during rolling, the billet will deform. And during this process, dynamic recrystallization may occur. And this process will contribute to smaller grain size. And between two rolling mills, there is a time interval, and during the time interval, the static recrystallization may occur. And this process will also change the grain size. And after rolling is a cooling process. And during this process, the phase transformation may occur. There will be the ferrite transformation, the perlite, bainite, or even multi-set transformation. And so we can control the cooling process to control the microstructure of the final products. Since we know there is a close relationship between the microstructure and the mechanical properties. If the mechanical properties of the final products are not satisfying, and we can perform further treatment, that is the heat treatment, and we also can simulate this process. And furthermore, if we want two parts joined together, that's the welding process, and to test the weldability, and we can perform the welding process simulation. Okay, these are mainly what we do with Gleeble. Now let's go to the details. And case study 1. And we just start from the continuous casting process. As I mentioned above, the cracks at the surface of the billet are our focus. And the cracks are mainly produced because of the low ductility of the billet during unbending process. And there are mainly two factors that will deteriorate the ductility of the billet. And one is the low melting point metals, and the other one is the precipitated particles. And these two factors can play a role in a specific temperature range. So it's very important for us to construct the relationship between the ductility and the temperature. And in that case, we can control the secondary cooling for the continuous casting process to get a reasonable unbending temperature and to avoid the cracks at the surface of the billet. Therefore, we just designed the following thermal cycle for the continuous casting process. And first, we will heat the sample to a very high temperature, and this temperature is just below the melting point, about 50 to 100 C. And at this temperature, the sample is in a semi-solid state. And after holding, it can be cooled down to different temperatures. And at this temperature, the sample will be tensiled to fracture. After the test and the data were collected, and finally we can obtain the following two curves. And one corresponds to the strength of the steel, and the other one corresponds to the ductility of the steel. Until now, we have determined hundreds of these curves for the steels with different chemical compositions, and we also constructed a database for that. And in fact, we've ever thought of constructing the relationship between the chemical composition and the ductility or the strength of the steels. But finally, we give it up because the chemical composition can play a complex role in the ductility or the strength of the steels. Hundreds of these data are far not enough, maybe thousands of that, or even more than that, and we can perform the further research to construct the models. Okay, this is our work for the continuous casting process. Now it's case study 2. It's about dynamic recrystallization, and it occurs during the rolling process. And in general, we perform the uniaxial compression test to study the dynamic recrystallization of the materials. And so, we perform the test on a low-carbon microalloyed steel. And the following pictures shows the typical flow stress curves from the test. And the flow stress curves to the left were obtained from the tested steel that deformed at the same strain rate, that 0.1, and different deformation temperatures. And the flow stress curves to the right were obtained from the tested steel that deformed at the same temperature, the 1000 C, and different strain rates. And here, I do not want to talk about the flow behaviors of the tested steel, and I just want to show you our research on dynamic recrystallization. And the first thing that we should know is when it starts, when the dynamic recrystallization starts. And that means we have to determine the critical conditions for the onset of dynamic recrystallization. And we cannot obtain it from the flow stress curve directly. Unfortunately, Professor Pollock and Jones have proposed a method, and this method is based on the relationship between the string handling rate and the flow stress. And with this relationship, we can obtain the string handling rate versus stress curve. And this curve, there should be an inflection point. And the inflection point corresponds to the critical conditions for the onset of dynamic recrystallization. And so we can obtain the critical stress or the critical strain. Therefore, we just use this method for the tested steel, and we obtain the following curve, following picture. And it shows the relationship between the string handling rate and the stress. And these four curves were obtained correspond to the tested steel that deformed at the same strain rate, that's 0.1, and different deformation temperatures. And on each curve, there is the inflection point. And the inflection point corresponds to the critical conditions for the onset of dynamic recrystallization. And so we can obtain the critical stress. And furthermore, we can obtain the peak stress. And it's easy for us to obtain the corresponding strain, and the critical strain and the strain corresponding to the peak. And finally, we collected the data and put the data in the same picture. And we can obtain the relationship between the critical stress and the peak stress. And by linear regression method, we can see the data points distributed along the line. And that means the critical stress is proportional to the peak stress. And similarly, we can obtain the relationship between the critical strain and the strain corresponding to the peak. And similarly, we can see the data points distributed along the line. And the critical strain is proportional to the strain corresponding to the peak. Okay, the next part, I want to show you an interesting curve. That is the flow stress curve in different coordinates. And first, let's take a look at the picture on the top. It's a typical flow stress curve from the test. Well, compared with it, the curve at the bottom exhibits a quite different shape. But in fact, these two curves are from the same data, and we should note, and the curve at the bottom is in a different coordinates, and this is the logarithm coordinates. And from the curve at the bottom, we can see there is a linear segment, and after linear, there is the inflection point. And this let us think of the thermal expansion curve. And on that curve, the inflection point corresponds to the phase transformation point. So, what about the inflection point on the flow stress curve? And we think it maybe have a relation with the critical conditions for the onset of dynamic recrystallization. And therefore, we just performed further research, and we used the method proposed by Professor Polik and Jones, and we obtained the inflection point on the string handling rate versus stress curve. And we also obtained the inflection point on the flow stress curve. And each inflection point corresponds to a stress, and we can compare the two stress. And it's interesting to note the results agree well with each other. And so here we just proposed a new method to determine the critical conditions for the onset of dynamic recrystallization. And we are not sure whether it's suitable for other materials, but at least it's suitable for the tested steel. Okay, these are the work for the critical condition for the onset of dynamic recrystallization. And the next part, I will introduce our work on the hot working equation. And I think most of you are familiar with this process, and so I just introduce this part briefly. And first, we just use the dependence of temperature, strain rate, and stress, and it can be expressed as follows. And these three formulas have been widely used, and by taking logarithm on both sides, and we can obtain the relationship between the process parameters and the material constants. And by linear regression method, and we can obtain the following pictures. And here I do not want to introduce the pictures one by one. And I just show you the results, show you the data process. And finally, we can determine the material constants. And with the assistance of the material constants, and we can obtain the hard working equation. And it can be expressed as following. And this equation is the hard working equation for the tested steel. Okay, the next part is about model for dynamic recrystallization volume fraction. And here we just use this model. And it shows the relationship between the volume fraction and the strain. And the key point is to determine the constant K and N. And this model is based on the flow stress curves. And we can take logarithm on both sides of this model 2 times. And by linear regression method, we can obtain this picture. And from this picture, we can see the data points distributed along the line. And the slope of the line is constant m. And constant k is related to the intercept of this line. And finally, we can obtain the model as following. And this is the model. And to test the validity of the model, and we put the curves from the model and the data from the experiment in the same picture. And from this picture, we can see the model can predict the volume fraction precisely. And so the validity of the model is confirmed. And here is the question. And do you think the flow stress curve could tell us all the information? And that is to say, whether the microstructure can be reflected on the flow stress curve. And from our research, it was found this model is not always suitable for other materials. And this will be our research in the future. Okay, these are our work for the dynamic recrystallization. Now, the next is case study 3. It's about static recrystallization, and it occurs during the time interval after deformation. And there are mainly 3 methods to evaluate the volume fraction. And the first is the metallographic observation, and we can perform the interrupt quenching test to obtain the microstructure. And second is the double deformation method, and we can perform the double compression or double torsion test. And the third is the stress relaxation method. And for these 3 methods, and the first one is time consuming, and the last one is a little hard to perform the test. Therefore, at present, the second method, the double deformation method, has been widely used. And for the double deformation method, whatever, the double compression or double torsion, and this method is based on the flow stress curves. Since we know the static recrystallization can lead to a softening, and which can change the stress or the strain energy at the second pass, which make it possible for us to analyze the flow stress curves to evaluate the static recrystallization volume fraction. And so there are several methods to analyze the flow stress curves to evaluate the volume fraction. For example, the 0.2% offset method, 2% offset method, back extrapolation method, 5% total strain method, and strain energy method. And last year, we published a work on the strain energy to evaluate the static recrystallization volume fraction. If you are interested in it, and I also can share that. And the following picture shows the methods to determine the characteristic stress or the characteristic strain energy. And since we do not have the torsion system, and our research are based on the double compression test. And so we perform the double compression test on a low carbon vanadium nitrogen microalloyed steel. And the following picture shows the typical flow stress curves from the test. And the flow stress curves to the left were obtained from the tested steel that deformed at 850 C and with a strain that is 22%, and we select different time intervals. And the flow stress curves to the right were obtained from the tested steel that deformed at the same deformation temperature but with a larger strain that is 35%. And from these flow stress curves, and we can see the stress as the second part decreases with a longer time interval. But with the time interval is longer enough, and we cannot observe the marked drop of the stress as second parts. And so finally, we can obtain the following pictures, and it's the results from the analysis of the flow stress curves. And it shows the relationship between the volume fraction and the time intervals. Let's look at the picture to the left first. And the two curves on top corresponds to the higher deformation temperature, that's 950 C or 900 C. And from these two curves, we can see the volume fraction increases with a longer time interval. Well, compared with it, the two curves below that correspond to a lower temperature, that 850 C and 800 C. And these two curves exhibit platforms. And that means the volume fraction will not increase with longer time interval. That also means the static recrystallization is inhibited. And compared with it, and we also can see that the platforms in the picture to the right. And we can see the platform is much higher and the time interval is much shorter. And that means the inhibition on the static recrystallization can be reduced by a larger strain. And to explain this, and we performed the interrupt quenching test, and we observed the morphology of the tested steel by the transparent electronic microscopy. And at first holding that's a short time interval, and we can only observe the titanium nitride. And with the longer time interval, and we can observe the titanium and vanadium carbon nitride. And the quantity of the precipitated particles increases with a longer time interval. Since we know the precipitated particles can play a penny effect on dislocation moment, and so it can inhibit the static recrystallization process. And with the data above, and we can obtain the following two diagrams, and they show the relationship between the recrystallization, precipitation, time, and temperature. And let's look at the diagram to the left first. And from this diagram, and we can see the recrystallized fraction changes at a small amplitude between the precipitated start and finish curves. And by comparing these two diagrams, and we can see an increase in the strain can lead to a shorter incubation time of the precipitates. Okay, this is our work on the static recrystallization. Now it's case study 4. It's about phase transformation, and in general, it occurs during the cooling process. And our work are mainly to determine the continuous cooling transformation diagrams. And generally, we say it's the CCT diagrams. And there are mainly two ways to obtain the CCT diagrams according to the process. And first, non-deformed austenite followed by a cooling that corresponds to the heat treatment process. And the diagram obtained under this condition is called static continuous cooling transformation diagram. And the second, the deformed austenite followed by a cooling that corresponds to the rolling process, and the diagram obtained under this condition is called dynamic continuous cooling transformation diagram. And our typical work on this part is to study the phase transformation behaviors of a low-carbon vanadium nitrogen microalloyed steel. And we studied the effect of deformation or the effect of holding time on the following things. And we studied the effect on the CCT diagrams, and we studied the effect on the microstructures, and the effect on the precipitated particles, and the effect on phase transformation temperatures, and microhardness. And to perform the research, and we just designed the following test schedule. And the test schedule was designed according to the hot working process in the real world. And there are mainly three processes. And first, the samples were reheated to 1150 C and held there for 3 minutes. And then it will be cooled down to different deformation temperatures. And here we just set 3 passes. And after deformation, it will be followed by a cooling to room temperature. And this is process 1. And second, in process 1, after deformation, the samples were held at the final temperature for 3 minutes before the cooling process. And this is process 2. And third, we just use the same process parameters from process 1, except for the strain. And we set the strain to 0. And this is process 3. And so after this test, and finally we can obtain the following 3 CCT diagrams. And the first diagram was obtained under the non-deformed condition, and this corresponds to process 3. And the second diagram was obtained under the deformed condition, and this corresponds to process 1. And the last diagram was obtained under the deformed followed by a holding condition, and this corresponds to process 2. And from these 3 CCT diagrams, and the following conclusions can be drawn. And from the 3 CCT diagrams, we can see there are mainly 3 phase fields. And so there are mainly the ferrite transformation, perlite transformation, and bayonet transformation. And we can see the deformation can promote the ferrite and perlite transformation. And finally, and holding at the last pass is favorable for ferrite transformation, which make it possible for occurrence of ferrite transformation, even if the cooling rate reaches 50 C per second. Now let's take a look at the microstructures obtained from the test. And the microstructures were obtained under a lower cooling rate of 0.5 C per second. And so the microstructure is mainly about the ferrite and perlite. And in this case, we can study the effect of process on ferrite grain size. And let's take a look at the first and second picture. And from these 2 microstructures, and we can see the deformation can promote grain refinement. Since we know deformation can lead to a increase in dislocation density, and which is favorable for ferrite transformation. And so we can observe smaller ferrite grain size in the microstructure, in the second microstructure. And from the second and third picture, and we can see the deformation followed by a holding also contribute to smaller grain size. And the ferrite grain in the third picture is the smallest compared with the other 2. However, since we know a holding will contribute to the recovery process or even the static recrystallization process, and this process will reduce the dislocation density, and so the nucleation side for the ferrite transformation can be reduced. And however, we just observe the smallest ferrite grain size in the last figure. And to explain this, I will perform the interrupt quenching test, and we observe the morphology of the tested steel by the transparent electronic microscopy. And these 3 microstructures shows the results. And from these 3 pictures, and we can see the deformation followed by a holding is favorable for the participation process. And the quantity of the participate particles increases due to the holding process. And since we know the participate particles can play a pinning effect on the dislocation moment, so it can inhibit the recovery process or the static recrystallization process. And this process will play a dominant role. And so we can observe the smallest ferrite grain in the last macrostructure. And this is one of the explanations. And here I want to show you another explanation. It's about the third generation thermomechanical control process. And the focus for this process is the precipitate particles, the titanium, vanadium carbon nitride. And it can precipitate at a higher temperature. And it can be the nucleation site for the ferrite transformation. But unfortunately, we cannot capture this macrostructure, and so I cannot present it here. And this is another explanation. Okay, the effect of process on phase transformation temperatures. Let's look at the picture to the left first. It shows the relationship between the ferrite start temperature and the cooling rate. And from this picture, we can see the ferrite start temperature can be enhanced by deformation or by deformation followed by a holding. And we can see the curve in red that corresponds to the process 1 is much higher, and the curve in green corresponding to process 2 is the highest. And furthermore, we can see the effect of cooling rate on the ferrite start temperature can be reduced by a deformation or the holding process. Well, let's look at the picture to the right. It shows the relationship between the balanced start temperature and the cooling rate. From this picture, we can see the balanced start temperature can be enhanced by deformation. However, it will be reduced by holding. And in this picture, we can see the curve corresponding to process 2 is much lower than the curve corresponding to process 1. Okay, the next part is the effect of process on macro hardness. And it can be divided into 2 parts, the lower cooling rate or the higher cooling rate. As the cooling rate is lower, and we can see the macro hardness can be enhanced by deformation, is curve 1, or the deformation followed by a holding, and curve 2. We can see curve 2 is the highest, and the corresponding macrostructure is the smallest ferrite grains. And so, the grain size plays a dominant role in the macro hardness of the tested steel. And when the cooling rate is much higher, and we can see the curve 3 exhibits a higher hardness. And from the macrostructure, we know the macrostructure is mainly about bayonet. And so in this case, the type of the macrostructure plays a dominant role in the macro hardness of the tested steel. Okay, this is our work on the phase transformation. So the next part is case study 5. It's about flow stress modeling. And here I just present part of the previous works on flow stress modeling. And from the 3 models below, and we can see the flow stress can be expressed by the process parameters and the material constants. And these 3 models have been widely used for decades of years. And from these models, we can see to construct the models, the key point is to determine the material constants. And the material constants can be obtained by regression method based on the flow stress curves from the test. Well, as the shape of the flow stress curve is concerned, it is hard to model for a typical curve corresponding to dynamic recrystallization. That is to say, it is hard to construct the model for just one formula. So here I just want to share our work on flow stress modeling. And first, let's take a look at the typical flow stress curve. And during the deformation, we know the hardening and softening occur at the same time. And with the increasing strain, the softening will play a dominant role. And when the strain reaches a critical value, and the dynamic recrystallization may occur. And after this, and the stress will reach a peak. And after the peak, the stress will meet a gradual fall to a steady state. And so, according to the deformation process, and we can obtain the characteristic points, such as the yield point, the critical point for the onset of dynamic recrystallization, and the peak point, and the steady state point. And so, based on the characteristic points, and we can obtain the segments of the curves. And then we can construct the models according to the segments. And here we just obtain 3 segments, and these 3 segments that fall into different strain ranges. And here the stress can be expressed by the characteristic points. And the following work is to construct the relationship, the process parameters, and the characteristic points. And the process parameters and the characteristic points can be connected by parameter z. And parameter z can be expressed as this by this formula. And so after this, we can use the strain rate, temperature, and the strain as the input. And then we use the mathematical models that we constructed. And finally, we can obtain the stress. And the flow stress can be regarded as a function of the process parameters. Okay, these are work on the flow stress modeling. The next part is the expansion of Gleeble. And first is the nozzle system development. As I mentioned above, and we had Gleeble 3800 in 2003, and we had 3 mobile conversion units: the universal system, Hydrawedge system, and MaxStrain system. And just as the name is, we often use the universal system. And for most of the tests, the cooling rate is one of the most important parameters. But unfortunately, there was no nozzle system on our universal system at that time. As we know, there are mainly 3 methods for the heat conduction: the thermal radiation, thermal conductivity, and thermal convection. And to enhance the convection, and we designed the nozzle system in 2008. And this picture shows the profile of the nozzle system that we designed. And the nozzle system could be coupled with the quenching system to get a faster cooling rate. And in the following parts, I will introduce some details about the nozzle system. And the nozzle itself has 2 parts. The nozzle itself has 2 parts, and there is a gap between the 2 parts, which can be adjusted to control the media flow. And in that case, we can control the cooling rate. And furthermore, there are 2 nuts attached to the nozzle, which make it easy for us to install and uninstall the nozzle. Okay, next part is the Anvil system development. And we designed Anvil system with 2 parts, and the anvils and the part to support the anvils. And this is the anvil, and this is the part to support the anvils. And for the anvils, we use the material with high strength at high temperature. And we can use the alloy steels from Ansteel. The part to support the anvils, and we can use the copper or stainless steel, and we can use other materials. That all depends on the thermal gradient that we want. And if we use the copper, and we can obtain faster cooling. If we use the stainless steel, and we can obtain the homogeneous deformation. And that could be compared with the ISOT Anvil system. Okay, the fixture design for the tensile test. As we know, we use the sample with ferrite on both sides for the tensile test. And as I mentioned above, and we performed the tensile test more than 1,000 times per year. As the number is concerned, it is a little hard to perform machining. And so we just designed the sample without ferrite on both sides, and we also designed the corresponding fixture. And this picture shows the profile of the sample and the fixture. And we have pattern for that. Okay, the next part is also the last part. It's about the quenching test method. Since we know, we perform the quenching test by spraying the water directly on the sample. And there are mainly two disadvantages. And the first is about Anvils. Since we know to spray the water on the sample, we also spray the water on the Anvils. And this will shorten the lifespan of the Anvils sharply. And another is about cleaning. And since we spray the water, and the water will distribute it all over inside of the vacuum tank. And to clean the vacuum tank is a little time consuming. And so there is a new method that proposed by others. I've ever tried that, and that is to take the sample out of the simulator to perform the quenching, to drop the sample directly into the water. But there is a problem. That is the adhesion between the sample and the Anvils. And if it occurs, and that will delay the quenching, in that case, and we can not obtain the microstructure that we want. And what we should do, and here is a solution. And here I want to introduce just one of the advantages of the induction heating system. And the quenching test, the problem occurred during the quenching test can be solved by the induction heating system. Since we know the Anvils for the induction heating system are not non-ferrous, and so there will be no adhesion between the sample and the Anvils, even at high temperature. So it is much easier to take the sample out of the simulator to perform the quenching. Okay, as the uniaxial compression test is concerned, and here I just want to make a comparison between the resistant heating system and the induction heating system. And for the resistant heating system, and generally we just use ISOTM system. And just as I mentioned above, there will be a adhesion between the sample and the Anvils. And generally we just take two measures. And first is to wrap the titanium foils on both sides of the sample. And second is we have to lower the temperature and to take off the sample. Well, compared with it, the induction heating system, we use non-ferrous Anvils, and so there will be no adhesion. And the sample can be taken off from the simulator even at a high temperature. And as the temperature gradient is concerned, and the temperature gradient is a little larger in the induction heating system, but it could be acceptable. And the following parts, I want to show you some typical flow stress curves that by using the induction heating system. And in fact, we ever make a comparison between the test on the resistant heating system and the induction heating system. And the results agree well with each other. Until now, the induction heating system have been in service for almost 2 years in Ansteel. Okay, this is acknowledgements. And these are all for my presentation. And thank you for your attention. Thank you.